conventional. An unconventional reservoir petrophysical model, 4-point porosity component model, total organic carbon calculation using different well logs, standard versus shale only density neutron comparisons, free and adsorbed hydrocarbon estimation using well logs, fracture analysis, permeability model, rock physics model and mechanical property analysis, and comprehensive petrophysical model. And I'll be using different examples worldwide, specifically Cambe shale from India, Barnett shale, Eagle Ford shale, Niobrara shale. So I'll be discussing case studies using these shales. So this is just brief introduction about well log. Well log, all of you are aware of well logging techniques. Well logging is a continuous record of measurement made in boreholes. In the subsurface lithology, this is the graphical representation of subsurface properties of the rocks with respect to depth. The total rock, it may be different, it may be comprised of different lithophases. It may be different types of rock types: sandstone, limestone, carbonate rocks, dolomites, limestone, then siliceous rocks like siltstone. So it may be of different kind of rock in the subsurface at different depth, as well as the thickness may vary from basin to basin. So what kind of lithology is present under the subsurface at 3000 meter depth or at 1500 meter depth that we do not know from the surface? So well log is one of the technique where we can differentiate the lithology. We can identify the lithology with respect to depth and what other reservoir. Our main aim is to identify the hydrocarbon reservoir. So we can differentiate reservoir as well as non-reservoir lithology using the logs. Then the reservoir rock, the reservoir formation, the whole formation may not be target for hydrocarbon exploration. That the whole formation is not the pay zone. So we can find out which zone is the hydrocarbon bearing zone and which is the water bearing zone. Then if it is hydrocarbon, then what type of hydrocarbon is present there? It is gas or oil that we can find out using the well log interpretation. So well logs are the graphical representation of petrophysical property of rocks with respect to depth. So these are in the second image, you can see these are common log types. Red color is indicating the direct determination. We can determine directly these properties: lithology, porosity, fluid types. You can calculate directly. And the green color is indicating that indirectly also we can find out this property using those logs. For lithology identification, you can use gamma ray log, spontaneous potential log, and indirectly you can get information from sonic, density, neutron, resistivity, nuclear magnetic resonance log. Porosity you can determine using sonic log, density log, neutron log, nuclear magnetic resonance, NMR log. Fluid type you can directly determine using density using resistivity log. Density neutron can also you have to integrate density neutron log. Then you can get information from wire line testing, wire well test. Fluid saturation, you can get information from density, neutron, and resistivity log. And for all these properties, you have to integrate core data. At the end, you can see core, using the core data at laboratory, you can analyze all those petrophysical properties. So for validate your well log data, or you have to you have to integrate core data, and to validate the core data, you have to integrate well log data. So integration of well log as well as core data is very important for petrophysical evaluation of a hydrocarbon reservoir. It may be conventional or it may be unconventional, but you require to do integration. This is basic workflow for log interpretation. You have to import the data, edit according to the software. Then you have to interpret qualitative interpretation. Then you have to go for quantitative interpretation. And after that, you have to calculate porosity, saturation, define log cutoffs. Then finally, you can do interpretation, stratigraphic correlation, structural correlation. Then finally, reserve estimation. So these are two sections taken from screenshot taken from Petrel. There are lots of softwares like Petrel, TechLog, IP, Geolog, PowerBands. You can use those software for analyzing well log data. You can import the well log data. Then in this image, you can see first image is well log location. You have to define the locations, import the data. Then the last, you can see the synthetic seismogram. you have to integrate seismic data along with the well log data. So first, let me discuss about the basic log, that is gamma, which is very important to identify lithology. What type of lithology is present there? It is sandstone, siltstone, or limestone. It is carbonate reservoir, or it is non-carbonate reservoir that you have to identify. So using gamma ray log, this is a very common log, and it measures natural radioactivity in the formation with respect to depth. It measures the radiation emitting from naturally occurring uranium, thorium, and potassium. High radioactivity causes the deflection in right, and low causes deflection towards the left. Here, this gamma log is displayed for different kind of lithology. For shale, it is showing high gamma. For sandstone, comparatively low. For limestone, it is comparatively low. For arkose, it is also showing comparatively low gamma. Then you can see variations for different kind of lithology. Total gamma gives what is the total radioactive element concentration present in that respective layer. And there is another advanced gamma log, that is spectral gamma, which give differential concentration of uranium, potassium, and thorium. This gamma log can be used as a proxy to identify different depositional environment. It can be used as proxy for depositional environment. You can identify what kind of depositional is present in that particular basin or that particular area, study area. Why it is important to understand? We'll be discussing one case study also. In that case, you will be able to know why it is so important to identify the depositional environment. So there are different shapes of gamma, and based on the shapes, you can identify what type of depositional environment it is indicating. Funnel shapes. First, you can see cylindrical shape. This cylindrical shape reflects relatively constant energy levels, and it can include it can represent aeolian dunes, low sinuosity distributaries, channels, and beaches. So the second one is funnel shape. This imply upward increasing energy. So it is showing coarsening upward sequence. In what kind of environment you can get coarsening upward sequence? Delta represents coarsening upward sequence. Deep sea fans and alluvial fan. This kind of sequence you will get. If there is this kind of sequence, then the gamma log will show funnel shape in the graph. Then if it is bell shaped, then it represents aeolian point bar, deltaic distributaries, and it also can represent deep sea fan or channels. Bell shape you can differentiate into symmetrical. It may be symmetrical if there is uniform, there is same kind of grains, or it may be serrated if there is thin shale intercalation with the sandstone. Then you may get the last signature. You can see serrated gamma. So this you can find when there is a gradation sequence and there is intercalation of thin shales within the sand layers. So these kind of signatures are important for sequence stratigraphy study also. The first one you can see, this is one example from North Sea. As already I have told you, natural gamma there is that can give total uranium, potassium, and thorium total radioactive concentration, and spectral gamma, which can give you differentiate between the radioactive elements uranium, potassium, thorium. Spectral gamma ray is the log which is particularly used when you are working in carbonate rocks or unconventional shales. Radioactivity caused by thorium, uranium, which is linked to clay content. While radioactivity caused by uranium, it can be associated with organic matter also. It can be associated with diagenesis, dolomitization also. For example, the second one you can see Niger Delta. Here it was found that there is high gamma ray value. So gamma ray value is coming for shale formations as well as sandstone formation also. So using only normal gamma, it was very difficult to identify what is the main cause of high radioactivity in this formation. But when spectral gamma was analyzed for the same zone, Here you can see using the spectral gamma, you can get differentiate value and you can identify what is the main cause of having high gamma. So in this case, this high gamma is coming because of different types of clays and heavy minerals. Clays, whatever the clays present here, mixed clay layers, kaolinite, elite is present here, and it is also coming due to gluconite, where you can see the feldspar line, and this is the clay line. So mixture of clays, different kind of clays, as well as feldspatic mineral also can give the high value of potassium, and which is the reason why you are getting high amount of gamma. So high gamma, it does not mean that only the radioactive elements are high. It may be due to organic matter, or it may be sometime due to feldspathic mineral also. In the first case, you can see high gamma in case of black shells. If there is black shell, then you will get abnormally high gamma, and that high gamma in this case, in case of North Sea, this is Upper Jurassic black shells of North Sea, where here this gamma is coming due to the presence of high amount of uranium concentration. So only total gamma cannot give you what is the reason it is coming from thorium or potassium, but if you use spectral gamma, then you can find out exactly the reason why it is coming because of uranium or it is coming because of potassium. That information you will get accurately. Then SP log. This is spontaneous potential. It records naturally occurring electrical potential, which is produced by interaction of formation connect water, conductive drilling fluid, and shell. SP curve reflects a difference in the electrical potential between a movable electrode in the borehole and the fixed reference electrode at the surface. SP has no absolute values, and does it treated quantitatively and qualitatively in terms of deflection only, which is the amount of curve moves to the left or it is moving towards the right, and that zero is defined, and definition of SP0 is called the shell baseline. It is made on thick shell intervals where the SP curve does not move. It shows zero value. So theoretical maximum deflection of SP opposite to the permeable beds is called static SP or SSP. In these three cases, A, B, and C, the first case A, where mud filtered salinity is less than formation water salinity, so SP is showing negative. For shell, low SP. For cleans, in this case, if it is clean sand, then it will show high SP. In case C, it is showing positive SP. SP is positive. Here, in this case, mud filtered salinity is greater than formation water salinity. So if it is shell, then it will show high SP. If there is clean sandstone, then it will show low SP. And if mud filtrate is equal to formation water salinity, then RMF will be equal to RW. RW is the resistivity of water, and there will be no SP development. So difficult to differentiate shale and sandstone in this case. And this SP log is also used to calculate shale volume. This is the equation how to calculate shale volume using SP log. SP log minus SP shale, whatever the SP present in the shale baseline. So SP log minus SP shale and SP sandstone minus SP shale. So I'm not going to discuss in detail about all these logs because all of you are, I think, aware of these logs. Still, I'll just give you a brief introduction. Neutron log, which will give you porosity value, neutron porosity, that is called neutron porosity. Neutron log measures the amount of hydrogen present in the water atoms of a rock, and it can be used to measure porosity. This is done by bombardment of the formation with neutrons, and it determines how many atoms are captured by the hydrogen nuclei. So when natural gas is present, become a big spread or crossover of neutron log and density log. Density, it shows density variation. You can see for different type of lithology, what is the variation of density. If it is coal, then it will show you very low density. If it is sandstone, you can see what is the density. If it is shale, it will show you greater density than the sandstone. Okay, if it is organic rich shale, then it will show very, very low density, just like coal. Coal will be the least density in case of coal. And using integrating all these logs, gamma, you can identify lithology, resistivity, you can identify what is the resistive formation. If it is hydrocarbon, it will show high resistivity. Then using density and neutron porosity, you have to find out where is the high porosity zone in that particular reservoir and where is the low density zone. If it is low than the normal density, then there may be some low density material, so it may be hydrocarbon. So you have to find out high porosity and low density zones. Here the yellow color zone is indicating hydrocarbon bearing zone. It is low density and high porosity zone, and you can see the crossover. Based on that, you can find out what kind of hydrocarbon is present. In the second case, this is oil. In the first case, it is gas. This is one case study I'm going to present. This is from India, and this is from Cambay Basin. This is a rich petroleum province in northwest India. Here, this is a rift basin, and there are lots of tectonic blocks like Sanchar Patan, Ahmedabad, Mehsana, Tarapur block, Bharos block, Narmada blocks. These are blocks based on, these are divided based on the rifting pattern. So there are lows as well as highs also in this basin. And this in this basin, uh, Cambay shale, this is the source rock. Older Cambay and younger Cambay. Kalol is the reservoir rock and Tarapur is the cap rock. This is the petroleum system, and you can see age of this petroleum system ranging from Paleocene, and the reservoir rock is this is from Eocene age. We have carried out log interpretation for this basin, and you can see first step that this is gamma, green color is showing gamma, and the second stake, this is resistivity rock, and the third stake, red color is indicating density log, and blue color is indicating neutron porosity log. So here you can find, you have to find out where are the low density and high porosity zone. So here high resistivity zones are marked with arrows, green color arrow you can see, and corresponding to those zones, you can see the low density, high porosity zones. So these are the probable hydrocarbon bearing zone in this basin, in this section. Again, for Kalol formation and for Mehsana formation, these are the first take, you can see gamma ray log. All the lithologies are displayed here. The yellow color is showing sandstone, black color, green color is showing shale, and black color is showing hydrocarbon bearing zones. High resistivity zones, you can see here, you can find out the high resistivity zones. These are marked with green color. You can see green color high resistivity zones. Then you have to find out now where are the low density. Density is showing by the red color, and you can see these are the zones. This one, these are the zone. I think you can see my cursor here. These are the zones. This one first one, and this is the second one where you have low density and high porosity. Then qualitative analysis for again the same. You can see this is this is sand. You can differentiate using the gamma, and this is high resistivity zone. And here you can see this is very low density and high porosity zone. Here density is extremely low and it is coal. Now stratigraphic correlation for the same study area. In the first case, we correlate Kalol top for all the wells, and for the second case we did structural correlation where we hanged at 1200 depth for Tarapur formation, and you can see towards right the thickness of Mehsana, thickness of Kalol formation is increasing, as well as thickness of Mandoli formation is also increasing towards east. So why this is important, stratigraphic correlation, this is important to understand what is the thickness variation, in which direction thickness of that particular reservoir sandstone is good, well, towards which direction reservoir quality is good. So you have to mark the boundary of that particular reservoir facies. For this, stratigraphic and structural correlation is very important. In this case, we have correlated pay zones, Mandoli top, different pay zones for Mehsana pay. You can see different pay zones, and you can see towards east side quality of this reservoir based on thickness. This is high. Pay zones thickness is high towards east. This is west east log correlation profile, and based on different well logged data, we map the pay zones, pay thickness, lithofacies map. And here in this second, in the figure B, these dots are indicating well locations. From these are the well locations, and based on the thickness of pay zones, we map the contours, we prepare the contours, and you can see lithofacies contours where the pay thickness is ranging from 2 to 12. So towards east side, thickness is increasing very high, and you can see the variation of the thickness. Okay. So now coming towards the conventional versus unconventional petrophysical model. Here we are considering two types of unconventional reservoirs. First one is tight gas reservoir, and the second one is gas shales or shale gas reservoirs. As unconventional reservoirs, these are very low permeable and effective porosity, very low effective porosity, and they are difficult to produce by conventional methods. And identification of these reservoirs are very difficult, and they show more affinity to shale because logs in this reservoir show more affinity to shale than sandstone or limestone on the log character. Sometimes they are misinterpreted. Sandstones are also misinterpreted as shale, and due to this character, quantification of porosity as well as water saturation in case of unconventional hydrocarbon reservoir is very challenging. Here, rock matrix, in case of conventional, these are the differentiation between conventional and unconventional reservoir petrophysical model. Matrix, this is composed of, in case of unconventional reservoir, it is composed of kerosene, and fluid can be present in the free form as well as adsorbed gas in the kerosene. It can be attached as adsorbed gas in the kerosene. And the other part of matrix is inorganic matrix, which is consist of dry clay, non-clay minerals. And here in inorganic matrix part, gas can be present as free gas. It may be bound water, and it may be clay bound water. It may be capillary pore bound water, or it may be clay bound water. So here 4 porosity component you have to consider. First one is effective porosity. Second one is porosity associated with total organic carbon, that is TOC. Third one is clay porosity, and the fourth one is free shale porosity. So unconventional petrophysical model, in case of this, this is very complex, and you have to consider all these 4 parameters. We will discuss how to calculate those porosities, and first let me show you what is the typical response in a conventional, typical log response in the unconventional reservoir. So here you can see this in the first step, it is gamma and dotted line, that is caliper log. In the second step, okay, let me find out the cursor. Okay. In the second step, that is resistivity log, and in the third step, red color is density log, dotted green color, the dotted blue color, this is neutron porosity log, and the dotted black color, that is photoelectric factor. So this is one example from Upper Shale Devonian Mississippian Woodford Formation of Oklahoma. And here the gamma is showing very high value, high resistivity for the typical shale section, and low density for this section. You can see density value 0.42 minus 0.15. very low density and very low photoelectric factor. As photoelectric factor is related to density only, so whenever you will get density, generally you will get low photoelectric factor. When density neutron log is recorded with a photoelectric curve, it is often called a lithodensity log. And in most density neutron logs run today with this kind of log. And uh, here you can see this is a typical high nuclear and sonic porosity, you can see, and this is a typical log display for a typical shale gas section. Now, as I have told you, the total organic carbon content is very important in case of unconventional reservoirs. So you can calculate TOC. As all of you know, TOC generally it is calculated in laboratory using TOC analyzer and rockable pyrolysis. You can use to estimate the TOC. So for that you require core samples. But unconventional hydrocarbon wells are not enough to get core data, and generally shales are present at in the subsurface at very high depth under the reservoir rock. So in most conventional fields where there is the well is not drilled up to the basement, so you will not get core data or cutting samples from that particular source rock. You will have limited wells to understand about the shale formations, which is acting as reservoir for the unconventional. So in that case, what we will do, we will take exploratory well core samples. We will analyze in the laboratory, and that one or two well data we will extrapolate and we will integrate with well log data. There are some numerical equations defined by derived by Pesce and Smoker. Here are the numerical equations. TOC you can calculate using delta log R into 10 to the power. This is the constant, and LOM, level of maturity. Delta log you can calculate using this equation where you require RT baseline, that is resistivity baseline, and you require phi value, porosity baseline. How you do define the baseline? You can see the steps. There will be the first step, it is not aligned with the baseline. In the second step, it is not in the line with the baseline. In the third, you can see these three logs are aligned with the baseline. So this is aligned with these two logs are aligned with the baseline. So you have to align the logs with the baseline, then you have to find out the value and you have to put in these equations. Then the log R density you can find out using this equation. So using these equations, you can find out log R value, then log R you can put in the first equation, then you will get total organic carbon content. Here the first graph is showing how to find out level of maturity. As in the equation 1, we have told that you require LOM value. How will you find out? That will find out based on delta log R value as well as total organic carbon content value. This is the standard graph. So whatever the value you will get in your study area, that you have to put in this standard graph, and you will get the LOM value. Then these are the cross sections for gamma versus deep resistivity, gamma versus rho B density, gamma versus porosity, and gamma versus DT. So here the circle, I have circled these are the zones where you have high gamma as well as high resistivity, high gamma, low density, high gamma, high porosity. So these are the phases where you can expect a good amount of total organic carbon content. These are the high resistive zones. Then this is another example where the TOC is estimated using the Pesce's method, and in the second case you can see this is here the TOC is calculated using Smoker's method. Equation is given here. Smoker's method is very simple. This is based on only, you can see, density. All these are constant, only density. If you have only density log, then also you can calculate TOC. But one thing you have to remember, that for that field, you should have at least laboratory generated data for at least one well. Then only you can integrate those data along with the well log data. In the first case, you can see the dotted, the graph, it is red color, that is the TOC derived from well log. And the black color line, these are the hot colors line, which is using, this is the zone, this is the hot color zone, which is indicating the increased TOC. Okay, so here now you can see all the other part, these two logs are aligned, but only the section, this is the zone where these two are not aligned. So you have to do the corrections. Based on that correction, uh, this is the well where you have both the data. You have their log derived data as well as you have laboratory derived data. So you have to do the corrections, and this correction you will apply throughout the field. So then only you can get accurate information or about the TOC data. So that is the reason why you should have at least for one data, because sometimes it may not be aligned, it may not be exactly same what you are getting in using the well log data. So if you have generated the TOC logs for all all the available wells you have, then you can prepare the contour map, and you can find out where is the sweet spot, where you have high amount of TOC content and where you have brittle zones. Based on all these parameters, you can find out the sweet spots. So in the first case, this is the example of TOC of Lower Eagle Ford determined using resistivity and bulk density log. So here, these red dots are showing the well locations, and you have generated data using well log for TOC data for these locations, and finally prepare the contour map, and this is the location where you have highest TOC value. So in this map, you are getting near Zavala and Frio. This is the high amount of TOC. This is the zone where you have high amount of TOC content. Then the second map, this is average of bulk density of Lower Eagle Ford shale. Here again the Zavala, this is showing the lowest density. This is showing okay, this one here, so it is showing the lowest density zone. Again, this one, TOC of Lower Eagle Ford determined using resistivity and sonic log. And how you can use, you can calculate TOC using resistivity and sonic. These are the equations, first and second equation. You can see, using this equation, you can find out the TOC. And again, in this equation also, you are getting the same, in the same zone, Javala and Frio. This is the zone where we are getting high amount of TOC content. In this graph, you can see the first is the gamma ray, then second, third, and fourth. These three are potassium, thorium, and uranium graph, and these three are derived from spectral gamma log. So using this spectral gamma, you can differentiate where is the organic rich zone. So here this gamma is high amount of gamma is coming due to uranium. Then for lithology identification, these are two standard graph. Second one you can use when you are working for shelly formations, only for shales, density Newton cross plot you can use. And this will help you to identify what kind of minerals are present in the shale. So you can use this standard graph to identify the lithology. Now, as I have already told you that calculation of water saturation, that is very important and that is very complex in case of unconventional shale formation. So here I'm giving you few equations only. Now there are lots of numerical equations, and these are some standard equations that I'm giving, which are using by different researchers. So the water saturation is, in case of unconventional reservoir, is completely depend on its organic matter, that is kerosene, and inorganic component, that is the minerals. As Archie's equation is popular for water saturation in clean reservoirs, but this equation you cannot use for unconventional reservoir. As the organic rich shale reservoirs have a higher content of total clay and organic matter, so corrections for true formation resistivity here is very important. So clay minerals, if because of the clay presence in the shales in high quantity, and clay minerals decreases the formation resistivity. On the other hand, kerosene increases the resistivity. So you have to usually you have to first you have to correct the two resistivity, and you can see in this graph this x-axis is RT true resistivity and y-axis is measured TOC. Now how we have derived these parameters? TOC, this is the equation 0.1635 into RT. Here if TOC is 100%, then we consider RT is equal to kerosene resistivity, that is RK. Then you can see this equation SW water saturation, that this is derived from lab. This is the equation, and this TOC is also derived from lab. So combining these both equations, you can find out water saturation. This is the equation with red boundary. This is the equation which is used for unconventional reservoir. Here uh, R T to resistivity and this V KR. This you can find from this below this two equation. You can see A is equal to V to K into RK. Here two resistivity is corrected in terms of subtracting a factor. Then that factor you can calculate using this equation. Then clay minerals effect on resistivity, you can correct using this equation. So combining with all this equation, this is the final equation for water saturation. Then another important factor is porosity. Porosity, we have done lots of laboratory characterizations of porosity for Indian shales, and here I'm not putting all these images, CM, microcity images here, because this time I'm focusing only on log data. But for estimation, scanning electron microscopy, microcomputer tomography, transmission electron microscopy, these are very important in case of unconventional reservoir. So here you can use advanced log like FMI, NMR for pore identification, but normal conventional logs are these cannot be used for porosity estimation in unconventional reservoir. So this is the equation, first equation. All of you are aware of this equation, which is used generally for conventional reservoir porosity determination, where phi D is density porosity, phi matrix, phi then bulk density, then fluid density. This is the common equation used for conventional reservoir. For in case of unconventional reservoir, you have to consider metric porosity as well as kerosene porosity. So for matrix porosity, this is the equation. Here Vk is the kerosene volume, TOC is total organic carbon content. In this equation, kerosene porosity, you can see TOC, this is the total organic carbon content, PV, this is bulk density, and PK, this is kerosene density. Here this is carbon conversion factor, and you have to calculate trans TR. This is the equation, and here hydrogen index, this is present hydrogen index, and HIO, that is original hydrogen index. So you can find hydrogen index again from the lab data. So lab data is also important in this case. Hydrogen index, oxygen index, that you can find using rock eval pyrolysis. And combining all these parameters, you can calculate finally, this is the equation which is used for porosity estimation using log data in case of unconventional reservoir. So this is the equation. It is with red boundary. This is the final equation which is used for TOC calculation in case of unconventional data. So I have already told you that for verification of and getting this parameter, hydrogen index, oxygen index, high present day condition, hydrogen index, and what are the original hydrogen index condition, for that you require laboratory data, that is rock eval pyrolysis. NMR, it has application in shale gas reservoirs, and again this is a vast topic. This is used for NMR. This is a very complex log, and it is a different topic. It takes a lot of time, but I'm just giving you application of NMR here. NMR, It is very important for unconventional reservoir, and main application includes measurement of porosity, quantification of kerosene volume, identification of fluids as water or hydrocarbon, determination of confining environments like organic kerosene pores and inorganic mineral pores, and it can also determine the bound water versus mobile fluid in the pores. So the principle of NMR log, NMR, it allows magnetic moment of hydrogen, which is abundant in rocks in the form of water. NMR signal amplitude is proportional to the quantity of hydrogen nuclei present in the formation, and it can be calibrated to give a value for porosity that is free for lithology effects. And this technique allows for determination of porosity, pore size distribution, permeability, water saturation, wettability. Generally, molecules in the fluids are constant, that is Brownian motion, diffusion about the pore space, and bounding of the grain surfaces. When interaction takes place with grain surface, then hydrogen protons can transfer some nuclear spin energy to the grain, contributing to T1 relaxation, and or irreversible dephase, that is called irreversible dephase, contributing to T2 relaxation. So depending on how often the nucleus collide with grain surface, this is the controlled by surface to volume ratio of the pore in which nuclei are located. So collision is less frequent in large pores, which results slower decay. Okay, and if it is high, then it will be opposite. So based on this theory, you have to understand about the pore volume and pore size in the in the unconventional reservoir shells. The another log, that is FMI, which is used for fracture analysis. So this is one new log. Now